All right, today we'd like to start by talking about quality control in fMRI, and this talk is about an overview and some of the lessons that we've been learned from the fMRI Open QC project. I have no disclosures. So what is quality control in fMRI? Well, this is something that's usually described in pretty minimal detail in most papers, and that's actually one of the reasons why we're here, trying to help make that better and more described in papers and also performed more broadly. So in general, what is quality control? Well, are we trying to find, for example, a good subject in a collection that we want to make sure that we use? Or do we have a glass is half empty point of view about it and say, are we just trying to find all the bad subjects in a data collection to remove them so we can do our analysis? And actually, we'd like to try to make the case here that probably what we're really getting at here is not quality control in the sense of filtering good, bad, and call it a day, but really we're trying to understand our data collection and everything that's in it as much as possible. And that includes understanding from the very beginning, making sure that the voxel sizes and the data types and all that we expect are there to start with and consistent across the group. And of course, looking for artifacts, but then also making sure that all the processing stages were reasonable and completed as they should have as well. Typically going through about the single subject level, what we might consider the regression model evaluation for fMRI. So this might include things like data consistency checks, checking the raw data, processing checks, and more. And then we also want to make sure as we're doing this that we don't end up wasting data. We don't just want to throw out a vast number of subjects in the name of questionable data if we don't have to. Of course, if we do have to, then that's a different issue. We don't want to bias the outcomes, and we don't want to leave QC until too late. So typically we would promote starting your quality control process as soon as you're acquiring your data or when you download a new data set from online. Each of these needs to be quality controlled essentially to the same degree. A lot of data that's put online is not necessarily curated, and also you don't know if when the curation was done, it was done in a way that's relevant to your study, perhaps, if you focus on one part of the brain or if you have one type of analysis in mind. Okay, so just as an example, thinking about starting the quality control process. So if we're given some information about a data set, what do we need to know about it to determine does it meet our expectations or not? So kind of is it good or bad, but in a looser sense. So if we get a data set of EPI that the average TSNR is pretty high and only 2 time points were censored, we might say, okay, great. And if we just wanted to stay with some quantities about the data set, we might be fine with that and move along. But maybe we should also look at the data set. Okay, well, that seems pretty reasonable. Well, maybe we should look a little deeper. And at this point, we see that there are some issues in this data set. So even though the average TSNR is quite high, there are regions where it dips pretty low. There looks like there's notable signal dropout here. And this creates really a problem. So in many analyses, for a whole brain analysis, we might say, well, this data set is problematic. We're going to have to remove this subject. But then again, we might also think, well, what if we only wanted to study the visual and kind of motor cortex regions that appear to be far away from this dropout? Then maybe actually this subject is okay to keep in our data set, and we should keep them there. So the kind of seesaw of decisions that we see here as we get different information, we really have to think a lot about what our study design is, what the goal of our project is, and then how the data can meet that. So we really have to think completely, start to finish, about our data set and what its goal is before we start the quality control process. And we also have to look at a lot of pieces of information. Here's another example. So in this case, the TSNR on average is even higher. There's only 7 time points that were motion censored, so those are both good traits. And now as we look at our whole brain of EPI, that actually looks pretty good. And then what happens if we look at seed-based correlation map that some quality controls use? Well, now we see that if we look beyond just the spatial information, but spatial temporal information, which is what the seed-based correlation maps have, this is not what a default mode network should look like. They're these large, weird, strong correlations and anti-correlations that can't be physiological across these tissue types. So in this case, as we looked more and more, things were okay, and then at some point this property showed the data really probably has some problems with it, so it might fail the quality control test. Okay, so these are just some things to think about, but hopefully this prompts the idea that quality control is important because there are interesting or weird or terrifying things in your data, depending on your perspective, and also that it's going to involve a lot of different types of quantities. So the project that we started here was called the Demonstrating Quality Control Procedures in fMRI, or the fMRI Open QC project. And here are just a lot of links for the background of the initial advertisement, which was open to everyone in the entire field. The data is still available. You can download it and look at it. And then the participating teams' articles and the overview and summary and editorial are all here. All right, so why was this project set up? Well, we've seen some reasons already, but here we go. First, we wanted to promote broader adoption of quality control across the fMRI field. So there's actually a lot of quality control tools and protocols out there in a lot of packages. So these are all open source packages and quite widely used. So there may be quality control protocols already in your software. You may not be aware of them, but they're there, and check them out. We also wanted to promote the idea of discussing quality control more in papers. Methods are unfortunately often underdescribed in papers, and some prestigious journals even minimize those a lot. But really, quality control essentially is part of your processing, and it should be described in detail, like your explicit list of quality control criteria and things like that. So this project wanted to put out a list of criteria from every team, plus showing a lot of examples, so to try to help the descriptive process. We also wanted to share detailed criteria across researchers and developers, so put more ideas out there in great detail for both users and developers. And hopefully this will help increase the amount of quality control across packages and have the discussion increase them to kind of new ideas in general. And finally, as we stated before, we really want people to think about QC not just as a simple good, bad kind of decision making about checking a couple properties of data set, but really wanting to make sure that the contents of the data collection are appropriate for the whole analysis and that they make sense, that they're consistent, and that there are no surprises in your data. And dare I say, this might even improve reproducibility across the field. Surely this is something that can only help towards that goal as well. But really, I think even more deeply than that, researchers should really understand the full contents of their data and how that ties in with their study, and that will really make the studies more robust overall. So how was the project set up? Well, we made a collection of real data. It was not altered at all, from task-based and resting state data sets from repositories that are available online and major repositories that people use, large consortia projects. And then we just asked anyone who wanted to form a team across their lab or collaborators or however, and process the set of data as they wanted to. There were about 130 resting state data sets and about 30 task-based data sets, so subjects. And then categorize each subject's data in one of the following ways. Did they think it should be included in a study? Did they think it should be excluded in a study? Or were they uncertain? Was it questionable about categorizing it and using it? And would this would be the kind of thing where typically someone would go check back with the acquisition or the DICOMs or things like that, but something where it wasn't quite easy to say include or exclude. And we asked each team to share a detailed list of all their QC criteria and then refer to it, both the qualitative and quantitative ones, as they decided to comment on their subjects and categorize them. And then we also wanted each of these drafts to be as didactic as possible. So we asked each team to share examples and images of all the categories of data of the interesting things that they're finding. So the different types of reasons why they would exclude a subject or call it uncertain, and also showing good data. What was the data that would be included and how did that compare to the others? So this is the project data. It can be browsed later, but basically it was 3 Tesla data that's pretty standard acquisitions, reasonable voxel size, kind of run-of-the-mill properties in terms of voxel size, TR, and things like that, from a lot of different projects in a lot of different places, just to have a broad scope of different kinds of data from different studies and things like that. So there were, the first 7 groups are resting state data, and the last group, the group 0, is task. And there were about 20 subjects from each of the resting state repositories used here, and so about 130 total, and then 30 from the task data set. So these are the list of papers. We had 10 participating teams overall, and there's fantastic work, and you can see here, even from the titles, that there's a lot of different toolboxes being used by each. And here you get a more detailed viewpoint. So in terms of both the software used for processing and the software used for quality control, these are a lot of packages, again, that a lot of people use. So hopefully this research topic set of articles is useful for all sorts of users across the field for getting more ideas about quality control, what to look for, and how to look for it in pretty good detail. So that was really the goal of the project, and it was great to see so many people using so many different software packages participate. Just as an example of the kinds of QC images and sometimes scary things that might exist in your data, there were checks for alignment, stimulus timing, motion effects, acquisition artifacts, all sorts of things. So check out the articles for a detailed description of all these. And what did the participating teams find? Well, across the 10 teams, in terms of looking at how many subjects were voted to be uncertain or to exclude, so for group 0, the task data set you can see here for a given team, some rejected or categorized as exclude quite a lot. And that's actually kind of the same across a lot of the data sets. It's really a pretty sizable fraction of the data sets were categorized as exclude or also uncertain, which could go either way, but really is something that, again, shows how much quality control and looking at your data is needed. I've never quite understood the argument of with big enough data, we can have a large fraction of subjects with quality control issues in there. It's really an important thing for studies of all sizes. And then for the rest of the 4 groups, really the story is about the same, that there were a large fraction of subjects in each case that were going to be voted to be excluded. And again, this is public data that's available, and some of it may be curated, but most public data is not curated. So when you're downloading data, you should really take seriously curating it for your own study there. All right, there were a lot of common themes across the teams. So each team found one or more subjects to exclude, usually quite a lot. So again, check your data, whether you're acquiring it or downloading it. And also check it with the view toward your specific study. If you're doing a whole brain study, that's different than focusing just on the motor cortex, things like that. Each team also did rate subjects' data as uncertain. And this is actually, in some sense, maybe the more interesting quality control rating to provide, because this is something that is going to lead to having to dig back deeper in the data. So now, again, going to this idea of quality control is not just about saying, well, drop some subjects, include some subjects, but really making sure that everything is understood in the data. And it could be that only one or two subjects are uncertain, but in digging back to figure out why they're uncertain, or even why some subjects are being excluded, that will tell you a lot more about the data, maybe something to fix, or maybe just something that hadn't been appreciated before. So quality control is probably a step in feedback and will lead to re-examining some of the acquisition properties. Nearly all protocols also check the raw data's consistency and the metadata. As anyone who's acquired data knows, it's very easy to change a setting at the scanner. When there's an upgrade at the scanner, things happen, the DICOM, the field of view, all sorts of things like this. Really, QC starts with the rawest of data that you can find and check and start verifying. And not to scare everyone, but, well, maybe to scare everyone a little bit, there were really some really kind of basic consistency, reliability, and mismatch errors that were found in some of the data. So two of the ones that were found were upside down EPIs. And if you don't notice this, now you have an issue in your study, certainly with brain regions aligning with other ones. But now when there's data consistency issues, this really raises the question of, can some of these be fixed? Because if the EPI is upside down, there's a problem with the header, and sure, you could rotate it, but can you trust left and right anymore at that point? And even in some other data sets, there were questions about left-right flips, and even about subjects being mismatched. A subject's anatomical and EPI appeared to have different sulcal and gyral features, so it's probably two different subjects mixed together in a data upload. So again, these are all things to really watch out for, because these will affect your analysis. Furthermore, in terms of the kinds of QC that people did, every team used qualitative criteria looking at your data, whether that was raw data or derived images like alignment or statistical maps. We live in a day and age of powerful computing, and people want to automate a lot of things. Checking your data still is really necessary in quality control. Every team here utilized it. It was just fundamental. And interestingly, you can see that not every team actually even used quantitative criteria. Really, the more fundamental one still remains qualitative. Quantitative criteria typically are derived from and kind of grow out of qualitative ones, so I have no doubt in the future that we'll have better ideas of what would be good quantities to check that's going to come out of qualitative views. And even as we have new data acquisitions, it'll be always quantitative checks that really lead the way in all quality control. So don't neglect those in your own study. What you should do is make those as systematic as possible and as kind of sensitive and efficient as possible for looking at your data. That will help your quality control. The QC parameters also, most every group discussed the fact that when you're evaluating something, you can't just say good or bad absolutely. It's always with regard to a specific analysis, like the example before of if there's dropout in one region but you are not focusing on it, then you can still probably use that data. And anyways, this is something that a lot of groups talked about in different ways, but this gets to the point that you really have to quality control your own data for your study, because your study has your hypotheses and your research goals in it. It may be fine to look at other people's quality control information as a start, but you'll probably always want to quality control your own data. And certainly non-EPI items can affect quality control. Certainly if your anatomical is not good for alignment, things like that. You may see that there are even physiological features that make you question some aspects of your data. Timing files, if you have physio recordings and things like this, all the inputs to your data really need to be checked. It's not just the EPIs for an fMRI study. And again, checked for consistency, not just on a separate level. And interestingly, and what was nice to see, is each team made their processing and QC pipelines publicly available. There's GitHub pages and websites that a lot of them link to. And so hopefully this will spur on more ideas for people reporting in great detail as well. So that's just an overview, and hopefully it sounds like something that would benefit your lab and your research group and your own data analysis and research. And we'll talk about this in a lot more details today. Thanks.